Hi, today we're gonna talk about segment tree bits. And no, don't turn off the video right away if you've read the blog on codeforces. I think I will be able to surprise you. Segment tree bits is a data structure, although I would rather say that it's not a data structure, but a high-level idea that allows you to solve a huge amount of problems that a regular segment tree can't handle. This data structure was developed by Ji in 2016, but outside of China, it became known only in 2018 after Rui wrote an article on this topic in English. After that, several problems were made on this topic, but it didn't become super popular. It seems to me that the reason for this is that the English article is very concise. As a result, it's difficult to really understand the power of this technique. I tried to explore this topic more deeply, tried to understand the original article in Chinese, simplify the proofs, and also add a few tricks of my own. I hope that after this video you will feel the true beauty of segment tree bits as I do, and this idea will finally enter the standard set of topics that are used in problems at various competitions. Let's go! It's gonna be an interesting journey. We will start with the basic techniques that a reasonable number of people know about, and then look deeper into it, and there we will find the most interesting things waiting for us. If you're sure that you're familiar with the basics, such as the G driver segment tree, you can use timestamps to jump directly to the moment you're interested in, or wait for the next video in which we will analyze other more advanced tasks. If you don't understand anything I said, you can use subtitles. They should be understandable. Let's start with a general idea of segment tree bits. What do we want to achieve? What does someone mean when they say the word segment tree bits? First, there is segment tree in the name. It means in fact that we won't build any new data structure. We will only modify the regular segment tree with segment update operations so that it will support more complex operations. A regular segment tree consists of two main components, the segment update function and the segment get function. For example, the sum on the segment. Let's call these functions update and get. Let's look at the general code of the update function. In general, this function takes as input the index of the vertex where we are standing right now, the left and right boundaries of the segment of the array that this vertex is responsible for, as well as the update query itself, the segment on which we want to change the value and the value we want to update the segment with. The change we want to maintain can be anything. For example, add this value to a segment or assign this value to all the elements on the segment. After that, we consider three options for how the segment of the current vertex is located relative to the query segment. Inside it, outside it, or it intersects it. In the first case, if it lies outside, then this change does not affect this vertex at all, so we can easily just stop here and do nothing. In the second case, if the segment of this vertex lies strictly inside the update segment, then absolutely all values will change on the segment of the current vertex, and we can easily recalculate the value at the current vertex, as well as save a push value, which we will then push into the children. Let's stick to the rule that if we are at a certain vertex, then the value of the function on the segment is necessarily correctly calculated in it. Sum, minimum, maximum, or something else depending on the task. So we should update the value in the current vertex, save the push value, and not touch the children yet. If we want to come to the children later and find out the value there, then we will go through the current vertex and push the push value down. And in the third case, if the segment of the current vertex intersects the query segment, but doesn't lie strictly inside it, we simply run recursive updates for the children of this vertex, making a push in advance. The children will correctly recalculate their values after the recursive call, and we only need to recalculate the value as the current vertex based on the values in the children. The get operation works in a similar way, but instead of changing value, we get the values. Let's refresh our memory on why this all works fast. This will help us in the future to understand more complex cases with segment tree bits. Let's look at each level of the segment tree separately. Each level splits the array into disjoint segments. We visit some of them for each level. Let's note that the third case, in which we run recursively in children, is possible for at most two vertices at each level. For a vertex that intersects the left boundary of the query, and for a vertex that intersects the right boundary of the query. So at the next level, we will call at most of 4 vertices, the children of these 2 vertices that we have on the current level. So at each of log n levels of the segment tree, we will visit at most 4 vertices. This scheme works great. With this segment tree, you can solve a huge number of problems. However, there are operations that it can't handle. Everything is built around the fact that in the second case, if the current vertex lies strictly inside the update segment, we can just stop here and quickly recalculate the current value. Of course, if we add on a segment, then the sum on the segment will be simply increased by the number of elements on the segment multiplied by the value that we add. If we assign on a segment, then everything is also very simple. However, for some more complex operations, this may not be possible. For example, if our operation squares all the numbers on the segment, how will their sum change then? It's not clear at all. This is where segment tree bits will help us. It says, okay, we can't recalculate the value at the current vertex right away, but whatever, let's go to the children. But if we always call from the children recursively, then we can potentially visit almost the entire tree, and operations will be performed in linear time, which doesn't suit us at all. So we'll do it smarter. We have 2 important conditions that will change. The first is breakCondition. It's the condition under which nothing will change on this segment at all, and we can safely finish our update here. The second one is tagCondition. That is the condition under which something changes on the segment, but we don't need to go to the children to recalculate the value. We have all the necessary information to update and return. So far, our breakCondition is a condition that the segment of the current vertex doesn't intersect with the query segment. And tagCondition is a condition that the segment of the current vertex lies strictly inside the query segment. This is not enough for us, so we will weaken the tagCondition and also strengthen the breakCondition, so that the asymptotics is not too bad. We will be watching for some potential function that will decrease when we do extra work, and this will mean that we won't have to do much extra work. Of course, the old conditions from breakCondition and tagCondition will not disappear, so we will need to add some more conditions to breakCondition after OR, and add some more conditions to tagCondition after AND. Most often, it's easy to understand what the breakCondition should be. Well, in which case the current change will not affect this segment in any way. In case of squaring all the numbers on the segment, this means that all the numbers on the segment are equal to 0 or 1, because these numbers don't change when squaring. To check this, you can store the minimum and the maximum on the segment and check that they are both either 0 or 1. But with tagCondition, everything is often not so simple. There are different ways to approach how you can leave an update in the current vertex without going to the children. It is the selection of the correct tag function that will be our main task. In this case, if all the numbers in a segment are equal, then it's easy to recalculate sum after squaring the segment. But in addition, we should of course not forget that we need to not just invent these conditions, but also prove that their time complexity is small. You may notice that we talked in detail about the update function, but didn't say a word about the get function. But the fact is that since we correctly update all the values at the update stage, nothing will change for the get function. It will work exactly the same as in a regular segment tree. Later in this video, we will look at a lot of different tasks and how to apply this technique to them. Any such task is determined by 2 things. What are the update queries and what are the get queries? Update queries can be, for example, plus equal, that is, add a value to all the elements on a segment, or just equal, that is, assign a value to all the elements on a segment. You are probably familiar with these queries, but in addition to them, we will consider many other unusual change queries on the segment, such as %equal, that is, for the input QL, QR, X, take all the elements on the segment from QL to QR modulo X, or divide equal, that is, divide all the elements on the segment by a certain number. There is also such an operation as max equal. It replaces all the numbers in a segment with the maximum of the current value and x. Similarly, you can do the min equal operation. We'll also look at the root equal operation. That is an operation that replaces all the numbers on the segment with the floor of their square roots. In addition, get operations are also very important. They can also affect the solution. Standard operations are find the sum, the maximum, the minimum, the GCD on the segment, and so on. I hope you're not tired yet. We move on to the first basic task. Using this example, we'll analyze in detail all the steps that we will be making with all other tasks so that we don't stop at them for so long in the future. Most of the problems that we will discuss in this video, you'll be able to solve in the contest that I've made for you. The link will be in the description. So, the first task. We have three types of queries. The first query is to take all the numbers on the segment modulo some number. This operation is called %equal. That is, we're given QL, QR, and X, and we must replace all the numbers on the corresponding segment with their remainder from the division by X. The second query is an assignment at a point. Given QI and X, we need to replace the element at a position QI with X. The third query is segment sum. QL and QR are given, and you need to return the sum on this segment. Queries of the second and third types are super standard. We won't have any problems with them. Get requests can be even extended. For example, you can add a get query for the minimum or maximum on a segment. But the query of the first type is unusual. We can just recalculate the sum on the segment if we know that all the numbers on the segment must be taken modulo some number. But anyway, when can we stop going down, and in what case do we not need to change anything? In other words, what will be the tagCondition and breakCondition in this case? BreakCondition is quite obvious. If all the numbers on the segment are less than our modulo x, then they will not change from taking them modulo x. In order to check this, you can simply store the maximum on the segment. On the other hand, tagCondition is more interesting. Let's note that taking the number modulo x is subtracting the number x from a several times until the result is less than x. More precisely, we subtract the floor of a divided by x times. Then, if for all the numbers on the segment ai divided by x are equal to some constant k, then kx will be subtracted from all the numbers on the segment, and we can easily handle it. This means that we need the floor of the division of all the numbers on the segment to be equal. This can be checked by comparing whether the floor of the division by x are equal for the minimum in the segment and the maximum in the segment. However, there's an even simpler condition that's suitable for this problem. If all the numbers on the segment are equal to the constant y, then all the numbers on the segment should simply be replaced by the floor of y divided by x. Well, we've come up with some tag and break conditions, and we can already write and submit this task. However, we still want not to just pass the tests, but also to understand why it actually works fast. Let's prove that this solution works in O of n plus q log n log c time, where n is the length of the array, q is the number of queries, and c is the bound for array elements. That is, at any moment, all numbers are less than c. Let's define the potential of the vertex of the segment tree as the sum of the logarithms of all the elements on the segment that this vertex corresponds to. Since the numbers can be equal to 0, for complete formality, let's take not the sum of the logarithms of the numbers, but the sum of the logarithms of the numbers increased by 1. Now, let's define the potential of the entire tree as the sum of the potential of all the vertices. At any moment, the potential can be estimated as O of n log n log c, because each element of the array lies in the logarithm of the vertices of the segment tree, and gives the contribution to each of them no more than log c. On the other hand, the potential is non-negative at any moment. Let's say that phi plus is how much our potential function will increase in total for all the queries. Later, we will estimate this number. Now let's divide the vertices of the segment tree that our query visits into three types: common, additional, and dead ends. Common vertices are the vertices that would be visited by a standard segment tree. Dead end vertices are those uncommon vertices where one of the break or tag conditions is satisfied. And the additional vertices are all the remaining visited vertices, that is, those unusual vertices from which we recursively code our children. Let's note that some of the top vertices of of the tree will be common, then there will be some additional ones under the common ones, and sometimes dead ends will stick out of the additional ones. There are no more recursive calls from dead ends. Note that the father of any dead end vertex is either a common vertex or an additional vertex. And each vertex has at most 2 children, so there are at most twice as many dead end vertices as there are common and additional ones. So visiting them doesn't affect the asymptotics, and we should only keep track of additional vertices. This could be understood a little bit differently. If we make a recursive call and immediately terminate, then in some sense we can assume that this recursive call wasn't made at all. Now that we have left only common and additional vertices, we'll prove that when we visit an additional vertex, then the potential at this vertex and therefore the total potential phi decreases by at least 1. Then the total number of visited additional vertices can be estimated as n log n log c plus phi plus. And we visit all log n common vertices for each query. At the same time, at each vertex of the tree, we do a constant number of operations, so the asymptotic of the algorithm will be equal to of n log n log c plus phi plus q log n. So we only need to show that phi plus isn't bigger than of q log n log c, and also that the potential decreases when we visit an additional vertex. Then we'll prove that our solution works as fast as we wanted it to. This explanation may seem complicated and confusing, but in fact, in the future, all the arguments about amortized time complexity will be similar to this. We are introducing some potential, we understand that it's always in the range from 0 to max phi, and we look at how much it can increase as well as how much it decreases when we visit additional vertices. From this, a conclusion is made about the time complexity of the algorithm. So, let's understand what phi plus is equal to. The mod operation can only reduce the numbers in the array, and the operation of the getSum type doesn't change the elements of the array at all. Therefore, potential increases can only occur during operations that assign an element. We changed one element of the array. It was at least 0 and became less than c. So, the potential could increase by a maximum of log c for each vertex in the subtree of which there is this element. And there are log n such vertices. The total number of queries is q, so the total potential will increase by a maximum of q log n log c, which was exactly what we needed to prove. Now we'll show why when visiting an additional vertex, its potential decreases by at least 1. If we visit an additional vertex, it means that we need to apply the percent equal operation to all elements on its subsegment. And at the same time, there is at least one number on the segment that is not less than x. Let's use the following well-known fact. If k is at least x, then k modulo x isn't bigger than k minus 1 divided by 2. This follows from the fact that if x isn't bigger than k divided by 2, then k modulo x is less than x, which is at most k divided by 2. And if x is bigger than k divided by 2, then we subtract something greater than k divided by 2 from the number k, so it becomes less than k divided by 2. Okay, if we visited an additional vertex, then some number on the segment will decrease more than twice, which means that its logarithm decreases by at least 1. Thus, we've proved that the potential of the vertex has decreased by at least 1. That's exactly what we needed to prove. Note that we didn't actually use tagCondition anywhere in this solution. Indeed, if it's not used, then the solution's time complexity will be the same. However, there is a harder version of this problem in which we assign the value not in the point, but on the segment. And in this case, our potential can increase by a lot. For this task, we definitely need the tagCondition we selected. However, I don't know how to prove that it works fast. I saw that in the analysis of the original problem, but I couldn't find the person who could prove it. If you know how to prove it, I will be happy if you share it in the comments. Let's look again at our idea. We defined some potential that somehow changes over time. You can imagine this potential as a pile of stones. Initially, it has some amount of stones, phi 0. We know that we will add a maximum of phi plus stones to it. The number of stones in the pile is always non-negative, and also when we do some extra work, we take a stone from the pile. This means that we can do a maximum of phi 0 plus phi plus extra operations. This is how we will prove all the asymptotics further on. Now let's move on to the second task. It's perhaps the most famous and even has its own name, Ji segment tree. We have two types of queries. The first type is min equal, that is, we're given QL, QR, and X, and we must replace all the elements on the segment from QL to QR with the minimum of the current value and X. And the second query is a get query for the sum on the segment. By the way, think about how you would solve this problem using a regular segment tree if the second query was a get query for the maximum on the segment. So, we have two types of queries. How will we solve the problem? Like before, we need to come up with tagCondition and breakCondition. Let's start with a simple one, breakCondition, in which case nothing will change during the min equal operation. If all the numbers on the segment are not greater than x, we can check this by storing the maximum on the segment. And what should be the tagCondition? In which case can we quickly update the sum value at the current vertex? Let's keep the maximum on the segment as well as the strict second maximum. That is, the maximum number on the segment that is strictly less than the maximum. Besides, let's also store the number of elements on the segment that are equal to the maximum. Then, if the number x lies strictly between the maximum and the second maximum, then only the elements that are equal to the maximum will change. And since we know how many of them there are, we can recalculate the sum. Max minus x multiplied by CNT max is simply subtracted from it. And we just save in this vertex that we need to push the min equal operation down. The important point is that we can take a composition of different pushes. If we first performed the min equal x operation on the segment and then min equal y, then instead of storing the push of these two operations, we can only store the push for the smaller of these two numbers. We'll prove that this solution works in O of n plus q log time. We will use the method of potential function again. We define the potential of a vertex as the number of different numbers on the segment for which this vertex is responsible. The total potential phi is again defined as the sum of the potentials over all the vertices of the tree. The number of distinct numbers on a segment isn't greater than the length of the segment, so the sum of the potentials at one level of the segment tree is no more than n. Thus, at any given moment, the potential is at most O of n log n. And what is phi plus equal to? During get queries, the array elements don't change, so their potential doesn't increase. In the first type of queries, the potential can only change for common and additional vertices, because for unvisited vertices, the values on the segment will not change, and for dead-end vertices, no values will be glued together. Either nothing changes when breakCondition is true, or maximum gets a little bit smaller but still remains bigger than second max. At the same time, for additional vertices, the number of different elements only decreases, because the two maximums are glued together, but it definitely can't increase. Therefore, the potential increases only for common vertices, with the only new value that can appear being x, because each element either doesn't change or is replaced by x. Thus, the potential can only increase in O of log n common vertices, and for each such vertex, it increases by at most 1. Therefore, phi plus isn't bigger than O of q again. Now we only should prove that visiting additional vertices reduces the potential of this vertex by at least 1. This follows from the fact that for additional vertices, x isn't bigger than the second max. So after executing this query, both max and second max will be replaced by x. That is, the two maxima will be glued together, so the number of different elements in this vertex will decrease by at least 1. Thus, the asymptotics of the algorithm consists of n log n, potential at the beginning, q again, potential increase, and q again from visiting common vertices. The result is O of n plus q again, which is exactly what we needed to prove. Let's note that similarly we can support the max equal operation and even their combination. It's enough to store two maxima, two minima, and their quantities. The time complexity will not change. In addition, you can add an assignment operation on the segment because, like min equal operation, it doesn't increase the potential by a lot. Let's move on to a more complex task. Most likely, if you read the article, you understood the solution of the previous problem. There is nothing complicated in it, but the solution of the next problem is already quite difficult to understand. I will try to explain everything in such a way that there are no problems with understanding. In the new problem, we have a plus equal on a segment query added to the previous queries. Actually, now we can support a very large range of queries. Min equal, max equal, assignment on the segment, plus equal, get queries for the sum, minimum and maximum on the segment. We've already had all the operations except plus equal, so we just need to figure out what to do with plus equal. But in fact, we don't have to do anything. The solution will not change at all. The plus equal operation is easy to add to the solution. Why then do we separate this operation from the previous task? And the fact is that the operation plus equal breaks our potential. Let's look at an example. We have an array of length n. Let n, for example, be equal to 8. The first half of this array is the numbers from 1 to n divided by 2, and the second half is also the numbers from 1 to n divided by 2. The root of the tree is responsible for the entire array. That is, its potential is the number of different elements in the entire array. At the moment, it's equal to n divided by 2. Now, let's make a query. Add the number n divided by 2 to all the elements in the second half of this array. In this case, our array will become 1, 2, 3, and so on, n. Now, at the root, the potential has become equal to n, because all the numbers are different. In all other vertices of the tree, the potential didn't change. That is, for one plus equal operation on the segment, we increased the potential of the tree by O of n. This does not suit us at all. So we will have to come up with a new potential with which we can correctly estimate the time complexity. However, we will prove a little bit bigger asymptotics. Not O of n plus q log n, but O of n log n plus q log square n. This time, the potential phi of the tree will be the number of its vertices for which the maxima in the left and right subtrees aren't equal. Let's say that such vertices are marked. Then it's obvious that at any moment, phi is at least 0 and no more than O of n. In what cases could the potential phi increase? If for some vertex, the maxima and the children used to coincide and then they began to differ. This could only happen if an operation was applied to the maximum in one subtree and not to the other. That is, the current vertex intersects with the query, but doesn't lie completely in it. This is definitely a common vertex. There are O of log n such vertices, so in one query, phi can increase by a maximum of O of log n. So phi plus isn't bigger than O of q log n. Now we will understand how the potentials decrease with the mean equal operation. We'll prove that if we visited m additional vertices in the mean equal operation, then phi will decrease by at least m divided by log n. This may seem weird, but in other words, if the potential decreases by k, then we will visit at most k log n additional vertices. Then the final asymptotics is O of n log n plus q log square n. Why will the potential phi decrease? Let's prove the following statement. In the subtree of any additional vertex v, there is a marked vertex u, which after applying the operation will not be marked anymore. Well, let's prove it. This is not difficult, but it's the key idea from which everything will follow. If vertex v is additional, then for this vertex maximum is bigger than x, and second maximum is at least x, because neither breakCondition nor tagCondition was satisfied. Then let's prove that in the subtree of vertex v, there is vertex u such that for it, the maximum in one of the children is max v, and in the other one is second max v. It will mean that now these numbers are different, and after applying the operation, both of them will be equal to x, so the mark will disappear from the vertex u. Why does such a vertex u exist? Let's look at the deepest vertex t in the subtree of v, for which both the first and second maxima are the same as for v. For vertex t, this condition is satisfied, but not for its children, because vertex t is the deepest such vertex. Then we can just notice that such vertex T is suitable as a candidate for U. On the segment of T, there is both max of V and second max of V, while in the children, there can't be both numbers, because T is the deepest such vertex. So all the maxima are in one subtree, and all the second maxima are in the other. At the same time, they obviously are maximums in their subtrees. Therefore, this vertex T is suitable for the role of vertex U, and there was a mark in it, and after applying the operation, this mark will disappear. Let's say that k marks disappear after applying the operation. Then all the additional visited vertices are the ancestors of these k vertices, because by the theorem we just proved, any additional vertex has a vertex in its subtree in which the mark disappears. Each of these k vertices has log n ancestors, so in total they have no more than k log n ancestors, which means that we will visit no more than k log n vertices, which was exactly what we needed to prove. The theorem that we proved is actually very useful for understanding the process that is going on, and we will use it again in the next problem. Let's move on to the next problem. Now let's add another operation to the ones we already have. Let us now have a query min equal on the segment, plus equal on the segment, and get query that should find GCD on the segment. It's a very unusual operation. Let's first understand how to solve this problem if we don't have the min equal operation, because even without it, it's not at all obvious what to do. Indeed, if a value is added to all the elements on the segment, it's not at all clear what will happen to their GCD. Let's think about how to maintain it. As you know, GCD of A and B is equal to GCD of A minus B and B. This is the fact on which Euclid's algorithm is based. That is, we can replace one of the numbers with their difference. But instead of replacing it, let's just add it. It won't ruin anything. GCD of A and B is equal to GCD of A, B, and A minus B. This fact can be generalized for more numbers. GCD of A, B, and C is equal to GCD of A, B, C, A minus B, B minus C, and C minus A, and so on. That is, the GCD of the numbers A1, A2, and so on, AK, is equal to the GCD of these numbers and all their possible k multiplied by k minus 1 divided by 2 pairwise differences. On the other hand, let's note that only a few of these numbers can be left out. It's necessary to leave only k of them so that their linear combination contains A1, A2, and so on, AK. And if these numbers can be obtained by linear combinations, then the GCD of such a subset will be equal to GCD of A1, A2, and so on, NK. Let's represent all the numbers as a graph. An edge between two vertices will correspond to their difference. Then, in fact, we only need to take some spanning tree of this graph, as well as any one of the numbers A1, A2, and so on, and k. Why? Let's take the number AI, as well as some spanning tree. How do we get a linear combination that's equal to AJ? Since we took a spanning tree, then between AI and AJ, in this tree, there is a path B1, B2, and so on, BL, where the first vertex is AI and the last one is AJ. Actually, all we need from the tree in this case is connectivity. Then in our subset, there are numbers B1 equal AI, B2 minus B1, B3 minus B2, and so on, BL minus BL minus 1. Their sum is equal to BL, which is AJ, and it's exactly what we needed to prove. Also, if our set wouldn't have the number AI, but only the differences from some spanning tree, then we won't be able to get the original numbers in this way, but all the differences. Again, we need to sum up all the differences on some path. Okay, but why did we need to prove it? Let's store on the segment separately any number from the segment, let's call it any value, as well as the GCD of all pairwise differences, div GCD, which, as we have already found out, is equal to the GCD of some spanning tree. And then the GCD on the segment will be calculated simply as a GCD of any value and div GCD. However, note that if we store such values at the vertex, then adding a number on a segment is no longer a problem. If the constant y was added to all the numbers on the segment, then the pairwise differences didn't change, which means that div-GCD didn't change either, and we also just need to add y to any value. Now we only need to understand how to recalculate the values of any value and div-GCD at the vertex using the values in the children. Any value is very easy to recalculate. You can simply take any of the any values from the left and right subtrees. And how to recalculate div-GCD? The div-GCD of the left subtree stores the GCD of some spanning tree of the left subtree, and the div-GCD of the right subtree stores the GCD of some spanning tree of the right subtree. So all we need to do is connect these two spanning trees, that is, add any edge between them. But we store any value for both subtrees. Let's take their difference. So the div-GCD for vertex v is a GCD for the following values: div-GCD for the left child, div-GCD for the right child, and the difference of any value for the left and right children. And then the solution will work in O of n log c plus q log n plus log c time, where c is the maximum value of the numbers that can be stored in our array. Note that in the second term, the logarithms are added, not multiplied, for the same reason that this happens in the segment tree with the search for GCD on the segment and assignment on the segment, because the consecutive calculation of GCDs of k numbers that are not greater than c by absolute value works in O of k plus log c time. This is a good exercise on understanding Euclid's algorithm. So, we learned how to support the plus equal and GCD operations on the segment. Let's add min equal to this. The problem is that with the min equal operation, even the GCD of pairwise differences changes in an unclear way. Let's change the concept a bit. We will maintain not the GCD of all pairwise differences on the segment, but the GCD of all pairwise differences of the numbers that are not equal to the maximum on this segment. And the maxima, as in the G driver segment tree, will be handled separately. Then, under the tagCondition, which as breakCondition is exactly the same as in the G driver segment tree, we can easily recalculate the values. We will only need to change the maximum, and div-GCD will not change in any way, because we only change the values of the maxima and they are not included in div-GCD. How do we then find the GCD on the segment knowing these values? All numbers not equal to the maximum are already combined into a spanning tree inside div-GCD. It only remains to attach the maxima, or one of them, because they are all equal to each other anyway. Second max can help us with this. Therefore, the GCD of the segment can be calculated using the following formula. This is the GCD of the maximum, div-GCD, and the difference between the maximum and the second maximum. The solution can be estimated as n log n log c plus q log square n log c by simply multiplying the asymptotics of the problem plus equal min equal by the logarithm of c. However, as in the previous problem, we can say that the logarithm of c can be not multiplied but added. Let's prove it. But why do we need to prove anything at all? Why can't we just say, like in the simple version of this problem, that the GCD of k numbers can be found in O of k plus log c time? The fact is that the GCD of k numbers that are not greater than c is calculated in O of k plus log c only if we calculate the GCD consecutively. That is, first we take the GCD of two numbers, then we take the GCD of this GCD and the next number, and so on. This is how an ordinary segment tree works. There we go down along the left and right boundaries of the segment, that is, along bamboos in which the GCD will be calculated consecutively. However, in segment tree bits, we visit a large number of additional vertices that do not form bamboos at all. So at first it seems like the logarithms will multiply, but let's dig deeper. Let's recall how we evaluated asymptotics in the min equal plus equal problem. We defined a potential to be equal to the number of marked vertices in the tree, that is, those vertices whose maximum in the left subtree doesn't coincide with the maximum in the right subtree. We proved that in total it can increase by a maximum of O of n plus q log n, and also for every O of log n additional vertices visited, this potential decreases by 1. So the asymptotics will be O of n log n plus q log square n. We showed that in the subtree of any additional vertex there is a mark that will be deleted. So if k marks were deleted, then no more than k log n vertices were visited. However, we are not interested in all vertices, but in those where branching occurs. After all, in Bamboo, as we have already understood, the GCD is calculated quickly, but all the additional vertices just lie on k paths to the root from the deleted marks, and on each such path the GCD will be calculated in of log n plus log c time. And since a maximum of n plus q log n marks were removed during the entire process, the asymptotics of this algorithm will be equal to of n log c plus q log n log c, implying that n isn't bigger than c, which is exactly what we needed to prove. The video is already a long one, so we'll stop here for today. We learned what the segment tree bits is and learned how to support min equal and max equal operations on a segment. Then we added the plus equal operation to them, and at the end we even learned how to count the GCD on the segment with these operations. In the second part of this video, we will look at even more advanced tasks with extremely entertaining ideas. For example, we'll learn how to support the divide equal and plus equal operations on the segment, or and equal and or equal, maintain a maximum of the sum of two arrays, each of which changes independently from the other, and so on. If you don't want to miss the second part, subscribe to the channel. But even now, you can find a link to a contest on codeforces in the description. There you can solve problems from this video. And also, there are gonna be algorithm codes in the description. Thank you for watching. Goodbye.